It doesn't take an expert to tell you that masonry construction is good construction. Ever since the first man made himself a shelter by fitting stones together to form walls, the world has accepted masonry construction as the most satisfactory and durable method of putting up a building. Construction engineering has worked hand in hand with architects and materials experts in discovering ever newer methods of construction. Yet masonry construction is still the bulwark of building today. Of course, the buildings being erected now are a far cry from the crude shelter that first stonemason erected, like this new department store in Washington, D.C. Yet, aside from the obvious beauty of design, the most fundamental difference between this modern masonry and the Stone Age man's crude shelter is in the masonry joints. Where the crude mason of ancient times filled his joints with mud and straw, builders now use mortar to tie the masonry units together. Of course, mortar does much more than merely tie masonry units together. It must also provide a cushion to absorb shock, prevent leakage when it rains, and resist the effects of extreme weather and temperature changes. There are many of you who I'm sure can offer many more requirements which masonry mortar must meet. However, I'm also sure that all of you will agree that just as masonry is good construction, good masonry construction needs good mortar joints. And I think you'll also agree that good mortar joints must have lime to be good. First, let's see what characteristics are most desirable in mortar joints. The first characteristic which any masonry mortar must provide is good bond. Now, we're not talking here of mortar strength. This quality in masonry mortar deals with its ability to bond masonry units together and to maintain that bond long after the building is erected. Next is weatherability. A masonry mortar should be able to resist high winds, freezing, thawing, wetting and drying cycles, if necessary, for as long as the pyramids of Egypt, which is the reason for this pyramid symbol. Our next symbol is going to seem a little strange in connection with masonry mortar, a rubber band. The point is that good masonry should have elasticity and flexibility. A good mortar should be able to resist the constant movement and stresses buildings are subject to, from wind, vibration, extreme temperature changes, and should be able to resist these stresses with little or no cracking and bond between mortar and masonry units. It should be able to give a little under stress and then restore itself to its original form. This brings us to the fourth characteristic. Adequate strength. We might better call this ideal strength, since good mortar should provide neither more nor less than engineering specs indicate for a specific job. This is very important, as you'll see in a few moments. Now, these characteristics are what construction engineers and you normally look for in masonry mortar, in the finished job. But there are more which are also highly desirable. Characteristics which are important during the job of putting masonry units into place. The first of these is workability. Good masonry mortar should be highly plastic and fill joints completely and easily, resulting in better quality workmanship. For this quality, we have chosen this bread and butter symbol, since, as any good bricklayer will agree, good mortar should go on the masonry unit with the same ease as warm butter. The last item, a sponge, is to remind us that good masonry mortars must have high water retentivity, so that they shall retain their water and resist suction or absorption by masonry units. There are many types of masonry mortar which produce many of these characteristics, but engineering tests have proven that the only one which will consistently provide all of them is mortar which contains an adequate amount of burned lime. Now, this should not be confused with pulverized limestone, which is inert and not cementitious. The use of lime in mortar is, of course, not new. Until the advent of Portland cement, lime was the only cementing material available for use in mortars. Back in the days when such buildings as Independence Hall in Philadelphia and many of the Harvard University buildings were built, construction proceeded at a leisurely pace. The slower set of straight lime mortars was acceptable. And were it not for present-day time requirements, straight lime mortars would still be highly acceptable for most construction. The fine condition of these buildings, which have yet to require tuck pointing after hundreds of years, attest to the durability of lime mortars. The reason for this long life lies in another characteristic of lime, which is known technically as autogenous healing. In every structure, regardless of how built, there's constant movement and change, sometimes caused by vibration, even daily temperature changes, and the more severe temperature changes caused by the changing seasons of the year. Now, these movements set up stresses which cause minute cracks in mortar. It's here that the phenomenon of autogenous healing goes to work to repair such cracks. Let me show you a simple illustration. This is a drawing of a highly magnified section of brick and mortar showing hairline cracks. When they occur, moisture, either from the air or from rain, and carbon dioxide from the surrounding air enter the cracks and cause a chemical reaction which creates a new lime deposit wherever the water and carbon dioxide can reach. In this way, the crack is closed automatically. The bond is healed, the moisture penetration is stopped, and the original strength is restored. This also minimizes efflorescence by preventing the solution of salts in masonry materials. Now, since this chemical action is very much like the formation of stalactites and stalagmites in limestone caves, let's use this symbol to represent the characteristic of autogenous healing in mortars using lime. Now, this pretty well outlines the most important of the advantages of lime in masonry mortar. However, in order to understand more fully how these advantages work together to affect an end result, an important study was undertaken at the Franklin Institute in Philadelphia dealing with the mechanical properties of mortar and brick. Since the primary interest is in the overall performance of masonry structures rather than any single component, the Institute studied mortar brick assemblages, thereby simulating actual structures. I have their report here. Let me read part of it. The tester used in this project was specially built for fundamental research studies. Brick assemblages were placed in a horizontal position and clamped at both ends. The assemblage is then bent back and forth at various speeds and through various distances. Two transducers are used to detect stresses and strains, and from their signals, the fundamental elastic and loss properties of the assemblages are calculated. When the stress and strain signals are plotted in an oscilloscope or XY recorder, hysteresis loops are formed. These differ in size and shape with the composition of mortars. The test program, carried out on assemblages 3 to 6 months old, showed definite differences in the mechanical responses of the assemblages. Basically, the early indications from these tests are that the high lime mortars have superior ability to adapt to mechanical strains and dimensional changes in the structure. That is, have greater flexibility and resilience. Well, that's pretty technical, but fortunately, we also have motion pictures of these tests, which make it somewhat easier to understand. Here's the equipment they spoke of in the report. Bars of bricks whose mortar joints had been aged for 3 months were clamped in a horizontal position for testing. The objective of the tests was to determine the amount of elasticity in lime mortars and their ability to withstand stresses. When stresses were relieved before the bars broke, they tended to move back to their original position, indicating elasticity in the mortar joints. When stresses were continued to the breaking point, the high lime mortar joints invariably broke through the joint itself. On the other hand, in similar tests made with low lime mortar joints, there was not only little joint elasticity, but when the bars broke, the joint separated cleanly from the brick, showing less positive bond. Here are the same bricks you just saw being tested. These are the ones whose joints were made with high-lime mortar, 129. Now, as you can see, the break here is through the mortar joint itself, indicating a high degree of bond integrity. Of course, it's nice to have these things proven for us in laboratories under exact engineering tests so that we can know exactly why these things work. Yet, many of these facts have been known to construction men for a long time. For instance, responsible industrial chimney builders have always used high-lime mortars. No other type of masonry is subject to such severe conditions. From wind pressure alone, a 375-foot chimney has been measured to sway as much as 2 feet each side of the center line under the force of an 80-mile wind. Added to this are the tremendous concentrated loads with settlement problems and the greatest exposure to elements externally and internally from the severe expansions caused by hot gases. For these reasons, the mortar must have sufficient elasticity to prevent cracking. That's why chimney builders use a lime-rich mortar of 1 part Portland cement, 2 parts lime, and 5 parts sand. A so-called stronger but more rigid and brittle mortar simply couldn't stand the gaff. Here's an interesting oddity which points this up quite strongly. Here's a chimney out in San Diego which was built in 1888, built with straight lime mortar. Improper foundation subsequently caused it to settle and tilt 5 feet out of plumb, like a U.S. version of the Leaning Tower of Pisa. This chimney stood for nearly 75 years right in the middle of earthquake country, a mute testimony to the elasticity, durability, and bond integrity of lime-based mortar. Now, this business of bond integrity, exactly what makes one mortar create a stronger bond than another? Let's see if we can't isolate some of the elements. Let's draw a line here to symbolize a cross-section of the surface of a masonry unit as though it were magnified. These little loops will represent the small cavities and uneven spots you can see in, say, the average brick. Now then, when a low lime mortar is troweled onto the masonry unit, it'll make excellent contact with the smoother surface of the unit. But unless the rough spots are unusually large, we'll not fill them in. However, when a good fat high lime mortar is used, due to its greater plasticity, it will fill every irregularity, providing a keying action which further strengthens the bond. But most important is this quality of high water retentivity. With a high lime mortar, water is retained within the mortar material, allowing the joint to harden and cure properly. With low lime mortars, the absorption factor in the masonry units tends to suck the water out of the mortar and into the brick. When the water is lost, the mortar loses its plasticity. Joints are difficult to tool. Bond integrity is reduced. Walls can become leaky. So much for theory. Now, let's take a look at some laboratory tests which will actually show the ability of high lime mortar to retain water. This is a standard ASTM water retentivity test. For comparison, the first test is with a straight lime mortar, 1 part lime to 3 parts sand. The initial flow was 105. The mortar is then placed in a suction device for 1 minute, after which the flow is measured again. This time, the flow is not much less, 99. The water retention value is 99 divided by 105, or 95%. Now for the lime Portland cement mortar. 2 parts lime, 1 part Portland cement, and 9 parts sand. The initial flow measures 103. The flow after suction measures 91, for a water retention value of 88%. It's interesting to note that according to National Bureau of Standards and the American Society for Testing and Materials specifications, minimum flow permitted after suction is 70%. The ASTM test you have just seen proves that high lime mortar runs well above this minimum. Another important element which comes to light in these specifications is compressive strength. In these days of competition between concrete and steel, and all of the new technological advances with pre-stressed concrete, some of the younger engineers and men fresh from universities where these subjects are being taught tend to forget the concept of this symbol here, adequate strength. What this means is simply enough strength to do the job plus an adequate safety factor. According to national engineering authorities, a mortar of only 100 pounds per square inch compressive strength is adequate to support a brick wall 9 stories high. This means that a 129 Portland cement lime mortar, such as you just saw, will give a safety factor in a 9-story building of 3.5 to 1, since a 129 mortar will produce a compressive strength in excess of 350 psi. This leads us to this symbol on the board, elasticity, the ability of a mortar joint to give a little rather than through too great strength to be brittle and crack under stress. Now, in addition to these two characteristics, which alone assure better masonry joints, we also have improved bond. Greater plasticity of high lime mortars plus high water retentivity assures a strong keying action of mortar to masonry unit and retention of moisture for the time necessary for the mortar to set. Then, because of the unique phenomenon of autogenous healing, high lime mortars afford strong weatherability. Stresses and cracks which may be caused by high winds, freezing, thawing, wetting and drying cycles, and extreme temperature changes are repaired automatically through autogenous chemical action of the lime in the mortar with rainwater and carbon dioxide in the air. The high degree of workability produced through use of lime and mortar brings about an almost automatic economy, a saving in time and materials, which is money in any man's language. The ease with which good fat lime masonry mortar can be troweled on the masonry units makes the bricklayer's job a pleasure. Jobs just seem to go up faster. Because of the consistency of a good lime mortar, there's less droppage. Masonry mortar materials go further. Because of lime mortar's high water retention, there's less need for retempering. Now, these are all advantages which can be gained through use of lime in mortar. How much lime? Well, ASTM specifications give many recommendations depending upon job requirements. As a good general all-purpose mortar, a mix of 1 part Portland cement to 2 parts lime and 7 to 9 parts sand by volume is recommended. This mix was used on the recently completed spectacular department store of Lord & Taylor in Washington, D.C. To provide impressively beautiful white joints, the contractor used white cement, hydrated lime, and white sand. But one of the greater advantages of lime mortars is that the proportions can be varied to suit any special condition. These mortar proportions are contained in the standard universally used specifications of ASTM and ASA. Only tried and true mortar materials are the safest to use. Yes, for strong, long-lasting, and beautiful construction, lime goes hand in glove with all types of masonry units, whether they are clay brick, concrete brick and block, sand lime brick, building stone, Indiana limestone, even glass block. And with these masonry units, it's used in all types of structures, ranging from skyscrapers like the United Nations and Chrysler buildings in New York, and this bank building in Denver, to this apartment in Kansas City, to modern shopping centers, to factories, schools, churches, to residential homes, to retaining walls. In all building structures, masonry has its place, and so does lime. You're wise to select time-tested masonry for your structure, both as sturdy and durable backup, and also to provide a veneer of attractive and weatherproof facing. When you design or build your masonry structure, be sure you specify or use lime in your mortar, and enough of it, so that your building endures.